So now we know why there's a need for spanning tree and how it works to prevent layer 2 routing loops, but we still don't have a complete picture. And to get that, we have to rewind a bit and find out why and how RSTP, Rapid Spanning Tree, which is 802.1W, improves upon the original 802.1D ST. In Spanning Tree, if the topology changes either because of a new link being added or a link being lost, then it can take between 30 to 50 seconds for Spanning Tree to reconverge. This is not the case with Rapid Spanning Tree. Previously, only the root bridge used to generate BPDUs, and these were then sent on by non-root switches if they received it on their root port. In Rapid Spanning Tree, these BPDUs operate like keeper lines being sent every 2 seconds by default by all switches. And if 3 of these keeper lives are missed, it will assume that the neighbor is down. Also, Rapid Spanning Tree can make ports forward rapidly if they are configured as either edge ports, like with the Spanning Tree Port Fast feature, or if the interfaces are configured as full duplex point-to-point links. So let's also compare the Rapid Spanning Tree port roles. We have a disabled port, which is a port that has been admin down and doesn't participate in the STP operation. Then there's the root port, which has the shortest path to the root bridge. Next is the designated port, which forwards and receives traffic due to having the lowest spanning tree path cost on a particular LAN segment. Then we come to the new Rapid Spanning Tree port roles. We have the alternate port, which provides a backup of the switch's root port. If the root port fails, the alternate port immediately transitions into the forwarding state and becomes the new root port. And finally, there's the backup port, which is a backup of your designated port if the switch has multiple links to a shared medium, like a hub. We probably won't get to see this one as hubs are no longer commonly used, but it's good to know. I mentioned earlier that the designated port forwards and receives traffic due to having the lowest spanning tree path cost on a particular LAN segment. This is usually due to the media type, where like a 10 gig interface is more preferred than a 1 gig interface, which is then more preferred than a fast Ethernet or a 100 meg interface. And this path cost can be manipulated with the spanning tree cost command. So let's jump into the configuration of spanning tree. Let's have a look at our topology first. This is the topology that we're going to be using. We've got QFX1 up here at the top, QFX2, 3 and 4. And I have the 4 switches already opened. So let me just look at that. We've got switch 1, switch 2, switch 3 and switch 4. Now what we should see is that on our diagram here now, XE001 should be an access port, and also on switch 3, and every other port on these switches should be trunk ports. Let's just take one by random. XE002 on switch 1, and it is configured alright. Actually, what I will do, I will go on switch 2 and we're going to configure these ports here first. So on switch 2 and switch 3. And what we find actually, if I'm going to configure those as host ports, to do any configuration on spanning tree, we do it under the edit protocols RSTP stanza, and we could configure those as edge ports. Now, if I was ever going to configure an edge port, you could configure spanning tree to ignore BPDUs on these interfaces where BPDUs shouldn't be received, yeah? And to do this, what I will do, I'll say set BPDU block on edge. And what this is going to do, it's going to stop any port that is configured as an edge port from receiving BPDUs. And this is for all of the ports set as edge ports. The only issue with this is once we've done this, if the port is blocked, it won't come up on its own without manual intervention. Then I can say set interface XE001 001, and we can set it as an edge port. And we could do the same on switch 3. We'll do it a bit of a different way on switch 3. So if I say edit protocols, rapid spanning tree, and we're going to say set interface XE001. We're going to set that as an edge port. But on this side, what we're going to do is we're going to set something called the disable timer. And what the disable timer is going to do is, if this interface is blocked, we're going to set a timer to say that it's automatically going to clear after a certain number of seconds. And we're also going to, instead of blocking all interfaces for BPTU block, which is what the previous command done, we're only going to block it for XE001. So if I go up and come out of this configuration and say edit layer 2 control for BPDU block, we're going to do the BPDU block just for this interface XE001, and we're going to set our disable timer to say if this interface is down for 180 seconds because it received incompatible BPDU, then after 3 minutes it's going to come back up. And that's the configuration. So if we now commit that here and commit it on the other side, if I do a show here, we can see that for interface XE001, if it receives an incompatible BPDU, then after 3 minutes it will come up. But that is not the same for switch 2. On switch 2, if it receives an incompatible BPDU, the interface will not come back up until there's manual intervention. Alright, and we could also do a command if we did want to clear those BPDUs. We could say run clear, I think it's error BPDU something for that interface XE001, and that will clear any BPDU errors on that interface. Okay, nice. Also, there's another situation, like say between switch 2 and switch 3, so it will be this link here. Maybe switch 3 was a older switch and it wasn't compatible with rapid spanning tree. Now, rapid spanning tree is backward compatible with spanning tree, but say if you didn't even want to run spanning tree, you can make this switch just run spanning tree, the original spanning tree, not RSTP. So, and to do that, what we will do is we'd say set, we're going to force the version to be STP. Now, the issue with doing this is that we don't get the advantages of rapid spanning tree. So if we set it as normal spanning tree, then it has to go through first the listening and then the learning before it transitions into the forwarding state. And we're going to get to see that on the actual switches. Let me have a look at the interfaces that are between those. So we're looking at XE003. What I can do, if I say run show spanning tree for all of the interfaces, at the moment we've only got spanning tree running for XE001, which actually I don't want to do, so I might actually disable that. Yeah, I will do. I will disable it going out to the, even though we've got it running as an edge port, which means that it will transition very quickly, and this is probably what you would do in production. For our lab environment, I only want us to see the spanning tree interface that we're interested in. I don't want any spanning tree operations running on XE001, so I will disable that. Let me do that first. For edit interface XE001, we're going to disable it, and this is only disabling it for spanning tree. And then let's go up, let's say a show. Okay, so we've disabled it, we've made the version STP. I'm going to commit to that on this side, and we're going to do the same on switch 3. So for edit protocols, rapid spanning tree, we're going to force the version to be normal spanning tree. And what I'm going to do, I'm going to commit it, and then we're going to count how long it takes to transition to the forwarding state. So it should go through learning and then listening, and then before it goes to forwarding. So I'm expecting 30 seconds. Let's show this. And let's commit. And after it's commit, we're going to have a look. Okay, so I didn't do it for that particular interface or something. Okay, let me have a look. Why is that not? Oh, because I haven't actually set the interface for spanning tree. So run shows spanning tree interface. None. So we're going to set interface XE003. That's the interface I want. Let's commit on this side and then do the same on the other side. Set interface XE003. And this is when I've done this commit, this is when we need to look at that command. Right. 1, 2. We're counting and we're waiting for this one to transition. So this must be the listening stage. Let's up arrow. See how long it's taking. Still listening. Now it's transitioned to learning. Still learning. Still learning. Now it's forwarding. And this is because it's using the old school original 802.1d spanning tree. So that's a good test. And what I'm going to do actually now, I'm going to remove that command, the normal spanning tree, and then we're going to have a look at rapid spanning tree. So let's delete that. Okay, and on switch 3, I'm going to disable spanning tree operations to XE001. Excellent. And what I'm going to do is just for all of the interfaces, I'm going to enable them for spanning tree. So we could say, sorry, up to come out of that, then set interface all. All interfaces have been enabled for rapid spanning tree. And I'm going to do that on all of the switches. Switch 1. I should have actually waited and seen how fast the convergence is. So we could probably do that on between switch 1 and switch 3. Oh, I've already done that on switch 3 and switch 4 I'm looking for then. Right, I'm going to commit here and then quickly jump over to switch 1, commit, and then say run show spanning tree interface. And we could already see that they're in the forwarding state. That's how quick it was. Even across to from link 3, it's already transitioned into the forwarding state. That's how much quicker rapid spanning tree is than normal spanning tree. All right, now we need to find out which one is the bridge. So the bridge will be the one that is forwarding on all ports. So this has a root port, so this cannot be the bridge. Let's have a look. But we can tell which one it is the bridge. So this is the port that is forwarding towards the bridge. So whatever this is connected to, so switch 1 is connected to XE002, which is switch 3. So is switch 3 the root bridge? Let's have a look. Yes, and switch 3 is the root bridge because all of its ports are forwarded and designated. Now, for what we wanted, we don't actually want switch 3 to be our root bridge. What I want to see is, let's say, switch 1 to be our root bridge. And the way that we could do that, just change that by the priority. So if I jump on here and I say set bridge priority to 16K, so it's 32,768. If we set it to 16K, then all of a sudden, we should see is that all of these ports should be turned to designated. I don't know X1, 2, and 3. I don't actually know why 4 is involved in spanning tree because we don't have a port 4, so I could disable that. Let's just disable that. And let's have a look at the show compare. So I've disabled XE004 and I've made the bridge priority 16K. What I should see is that 004 just disappears from our spanning tree and that these 3 transition to designated, and that should happen almost instantaneously. So let's see if I do a commit. Run show spanning tree interface, and they're already transitioned into designated. So this is now the root bridge. And if we run over here onto switch 3, and we can see that that has a root port. That is excellent. Okay. The last thing that I wanted to show us in regards to spanning tree is changing our root cost. Now, if I run again onto switch 3, run show Ethernet switching table, we're seeing that we're learning our host from XE001, which is what I expected to, and also switch 2 Switch 2 isn't learning anything through spanning tree at the moment, which is not what I expect. So that's probably, let's have a look. Why is that? Switch 2. Interface all. XE01. I would expect this to be partaking in spanning tree. Let me get rid of some of these. So edit. Delete. Interface XE003, don't know how I say it, and delete this BPDU block on the edge. Delete. Also, let me have a look if it's what ports are participating in spanning tree. Sorry. So all of its ports 3, 2, and 4. 2, 3, and 4. Yeah, that's what I expect. Let's commit that. And let's do a ping from the host. So I will open up host 1 and I'll ping across to host 2. Oh, switching to Cisco. The ping is successful. Okay, excellent. And now let's jump back onto switch 2 and see if we see anything in the switching table, which we do. Excellent. Now, what I was trying to say previously is that we are learning the MAC address for host 2 through XE002. So the path is following, coming into switch 3, going up to our root bridge and coming down and across. That's the path it's actually following. Let's say we didn't want it to follow that path. Now, as long as none of these ports are blocking, we could probably make it go this way. So I will check which ports are blocking or make it go this way, depending on which, as long as it doesn't have to pass through a blocking port. So let's see if we can manipulate that and change the path. So what I want to do on switch 3, if I jump onto edit interface XE003, run show spanning tree interface, we can see the cost is 2000 going through port 2. If we say that our exit cost for port 3 is something low, like say 300, then it should change the path as long as one of the paths isn't blocking. If I say set cost 300, let's commit that. This cost is 300, and let's see if it has changed on switch 2. Well, it hasn't changed at the moment. Let's run clear Ethernet switching table. So this is actually a blocking port, so I don't think that will actually work. It messed up, so I just took a reboot. Now, to actually reevaluate the cost values, I'm having a look on switch 2 and I can see that switch 2 has 2 ports that are blocking. To get around this and actually show you the cost, what I'm going to have to do, I think, I will have to reduce the priority of switch 2, make switch 2 the root bridge. That's what we're going to do first. Hopefully this works. Edit bridge priority. Set bridge priority. Let's make that 8K. That's the first thing. Let's commit that and see if that is propagated throughout the other switches. Let's jump onto switch 4. Now we can see that the bridge has a priority of 8K is what we're looking for. Now run show Ethernet switching table to see which port I'm learning the VLAN. So I'm only learning my own host, which is connected to me. So let me ping across the link again. Ping 192.168.0.2, which is pinging. Now I should see that in switch 2's MAC address table, which I do, and it's learning it through the correct MAC. Okay, so the cost did actually work when I changed the bridge priority. So previously it was learning it through XE002, maybe somewhere up here. Yeah, previously it was learning it through XE002. When I changed the cost when I change the cost on switch 3, it stopped advertising it via XE002, which went up and down, and started advertising it through XE003, because there's no blocking ports between switch 2 and switch 3. Whew, that was a bit of a longer one than I thought, but thanks for watching, and let's move on to the next video.